right, hello class. Today will be our final lecture in linear responding systems. We have over the last few weeks talked about time-dependent response within a linear responding framework, essentially envisioning that we have some system for which we know a lot about. We can compute correlation functions either in time or space, and we ask if we take that system and perturb it initially in the first part of this class by a static perturbation and subsequently with a time-dependent perturbation, we now know how to relate low-order measures of the structure or dynamics like spatial correlation functions or time correlation functions to that subsequent response. Most recently, then, we have focused on modeling time correlation functions in systems for which we would like to understand their dynamic response. And this has led us to linear models of dynamics like the Langevin equation, its generalization, and most recently to equations of motion for probability densities. So that's what I would like to review a little bit before we confront the main topic of today, which is taking some of those ideas into the quantum realm and writing down equations of motion for open quantum systems, so quantum systems that can exchange energy with their surroundings. So from some of the last lectures, the very first lecture on dynamics, we worked out that an implication of Hamiltonian mechanics was that a classical system has a so-called incompressible phase space. That's a fancy way of saying that if I ask for the time dependence of the probability of viewing a microstate X, where X is all the positions and all the momentum of all the particles, that time dependence is completely encoded by the action of a linear operator on that probability. So this was valid for deterministic dynamics. The kinds of dynamics you learn in some of your first physics classes, F is equal to ma. And this linear operator told me I needed to know what dictates the rate of change of, say, the momentum, and then I take a gradient of that momentum, and I need to know what determines the time dependence of the position, and I take a gradient with respect to that position for all n components of my system. Acting that on the probability distribution lets me evolve that distribution of microstate points. This is a way of showing, as we did, that if I start in a Boltzmann distribution, a distribution for which microstates are sampled in proportion to the exponential of minus beta, the energy of those states, that distribution is stationary. So this is Liouville's equation. In some very strict sense, last lecture, we derived the equivalent, how we move probability in some phase space, again, for the microstate of some system. But now in a case where the system can exchange energy with its surroundings. And what we found was that the form was conserved. There is a probability, there's an equation of motion we can write down. That was valid for this stochastic dynamics. Stochastic because the bath, in allowing it to exchange energy with the system, the degrees of freedom that I'm following, imposes random forces. So for example, in the equation of motion known as the Langevin equation, in which I have a deterministic force, but in addition, a frictional force and a random force, we derive the so-called Focker-Plunk equation. Which says that the update rule for moving my probability distribution depended on the gradient with respect to the momentum, a combination of the drift terms that can move that system around due to external or intermolecular forces, this frictional force. In addition, there's a gradient due to the spatial degrees of freedom that just depends on the momentum. And finally, there was a piece reflecting the ability to allow energy to diffuse away, which generated a second derivative, in this case, with respect to momentum. Oh, and I've done it again. I've used P's for momentum and for probability. All right, let's fix that. So as stated, this is the so-called Focker-Plunk equation. And again, it should be thought of as the equivalent to the Liouville equation in the way that the microcanonical ensemble is an equivalent restatement as the canonical ensemble, in that they encode the same sort of information in the right limits. So again, to get the Focker-Plunk equation, or the underlying Langevin equation, whose random realizations when averaged over give us the Focker-Plunk equation, we assume that there was a large bath for which that system that we were following was weakly coupled, and thus admitting the exchange of energy without having to worry about moving the bath away from equilibrium. And not surprisingly, not only is the Focker-Plunk equation parameterized by the forces that act between particles, the masses of those particles, but in addition, there is explicit temperature dependence that enters in, reflecting the fact that the bath is kept at equilibrium at that fixed temperature. So these are both equations of motion on a phase space, on a space of positions and momentum of particles. It is a natural question to ask, is there a quantum equivalent? Can I write down the probability distribution and how it changes in some way that is kosher with quantum mechanics? So acknowledging that I probably can't specify positions and momentum at the same time. Turns out that that's true. Many of you probably have seen the so-called von Neumann equation, an equation of motion for the density operator or the density matrix. So that will be our first task, is to derive the closed system equivalent of Liouville's equation for quantum systems. And having done that, we will then follow a very similar path to our derivation of the Langevin equation. So assume that this quantum system now is in contact with a bath for which it can exchange energy, treating that to second order in the interactions between the system and the bath. So assuming that the bath interacts weakly and that it responds linearly, we will get an equation of motion for the probability distribution for the open quantum system, and thus be able to actually describe relaxation in a way that a conservative equation, an equation in which energy is conserved, cannot. Okay. All right, so let's start by defining first really what we mean by a probability distribution in a quantum mechanical system. So let's consider an excuse me, let me take a drink. Let's consider an operator which is an outer product of the time-dependent wave function of the system. And let's define that operator as rho hat. Now, within some basis, I can expand that operator, inserting resolutions of the identity and corresponding coefficients. I can write that operator however I like. Here envisioning that state of the system, psi, can be expressed in that expansion. An element of that operator, so that is a operator quantum mechanically, has an interpretation as a matrix. Indeed, we see that it has an n and mth component. The n mth component can be computed by taking the inner product of that operator, which pick out those specific coefficients in the original expansion of the wave function. Now, the fact that the wave function starts normalized is tantamount to saying that if I sum overall n, the magnitude of C at all times, that is equal to 1. And thus, the trace of rho must be equal to 1. Okay, so this is at this point a definition. We're calling it a density operator, or which has elements of a so-called density matrix. Why is this akin to the probability distribution that we operate with classically? Well, consider now taking an expectation value of an arbitrary quantum operator A, denoted as usual with brackets. These could be time dependent. A quantum expectation is given by an inner product like so. Again, expanding those wave functions with the C coefficients we've introduced previously. I note that that expectation value can be written by substituting in what I just found for my density matrix as those elements, C, N, M, like so. So indeed, a quantum expectation value is given as a sum over a weighting factor, in this case, rho nm times the quantum expectation value, the element-wise operator A. This is the typical form of an average that we find in classical systems, where that rho thus clearly plays the role as a probability. Put very compactly and analogously to a classical system, we can say that a quantum expectation value is given by the trace of this density operator and the operator whose expectation I'm trying to compute. So element-wise, the density encodes the weights of an expectation value. The analogy or the analog of an integral over phase space is a trace operation over all the elements of my matrix. And thus I see that indeed a reasonable identification of this density matrix is the quantum analog of the probability distribution. But unlike a classical system, this density matrix is an operator. So if this is the analog of the probability distribution, we might ask, well, how do we write down its time dependence in a manner that is analogous to the Liouville equation? So this can be found straightforwardly. If you remember your basic quantum mechanics, operators evolve with a Heisenberg equation of motion. A simple way to, to derive that equation of motion is to ask explicitly for the time dependence of rho hat and substitute in, these are not partials, these are full, and substitute in what I mean by the density operator, which is that outer product. Through the chain rule, I will have a derivative of both the bra and the ket. And I know how the bra and kets each evolve in time. That's given by the time-dependent Schrodinger equation. So substituting those in, the generator of motion is the Hamiltonian acting on that wave function up to factors of I and h bar. That's in the forward direction. I can also write down its adjoint, which is its complex conjugate, if it's going to act to the left. And thus, compactly, I find that the evolution equation for the density matrix is given by a factor of I h bar and the commutator of the Hamiltonian with the density matrix. That is a linear operation for which we can denote an operator L acting on that density matrix. Often that L is denoted a so-called super operator because it's not like your old traditional operators. It's an operator on the space of operators. An operator is a linear operation like a matrix vector multiplication. Here we have a commutator that is rolled up into the definition of our operation. Nevertheless, it is a linear operation. But just to distinguish typical operators like the Hamiltonian from our equivalent to our Liouville operator. So indeed, this is often called the quantum Liouville operator. And this equation is known as the von Neumann equation, or alternatively, the Liouville von Neumann equation. It can be integrated exactly and straightforwardly. I guess usually the I is left out in front. Like so. And what we mean by that, like any Heisenberg representation, is that we sandwich propagators around that specific operator. One should be a little bit careful. What I mean by that is rho 0. All right, so this is the closed system equivalent, quantum mechanically, of our Liouville equation. Tells us how, having identified the relevant operator that tells us about expectation values when I trace over them, we now have an equation of motion for telling us how that density matrix evolves in time. And it's determined uniquely by the Hamiltonian in a way that the Liouville equation classically is analogously determined uniquely by the Hamiltonian. Okay. So that's the closed system equivalent. Now we want to open the system up. Let's try to write down an equation that can actually relax, that doesn't just contain these phases and thus conserve energy. The fact that evolution in the von Neumann equation occurs just through a rotation in the Hilbert space tells you that everything is, energies are conserved, norms of phase spaces are conserved. Let's see what happens if we take a system of interest and interact it weakly with the surrounding bath. In doing so, we will work out essentially a linear model for quantum relaxation. So the picture we're going to have in mind is that we have some density matrix to start with. Which reflects not only some degrees of freedom we're interested in, who span some Hilbert space, say denoted by this green region, but in addition is coupled to a set of harmonic oscillators or Gaussian variables, each of which has their own Hilbert space. We're going to trace out the harmonic variables. So these are representing harmonic oscillators. And arrive at an equation of motion on some reduced space. If the full space is denoted with rho of t, the reduced space will be denoted with sigma of t. For which that is the only explicit part of the Hilbert space we'll monitor, but its evolution will be influenced now by a parameterization of that bath, of the harmonic oscillators we've traced out. Let's denote those degrees of freedom rho b. We need to describe how the bath influences our system. So this sigma, if rho is the density matrix, sigma is what's known as the reduced density matrix. Reduced because it spans only the part of the Hilbert space that we're interested in. All right, that's the picture. Now for the math. Let's set it up in the same way we set up our classical calculation previously. Consider a Hamiltonian that can be broken up into three pieces. A piece that tells us about the system, those green degrees of freedom. A piece that tells us about those harmonic oscillators, the bath degrees of freedom. And if there was nothing else, if they each lived in their own Hilbert spaces, then of course the system and bath would evolve independently. So we have to have some coupling, call it V, that's going to then describe the interactions between the system and the bath. To make things tractable and simple, let's imagine that that coupling takes the form of a Kronecker product or tensor product between an operator that lives in the Hilbert space of the system, S, and a linear displacement in the harmonic degrees of freedom. So HB is a set of harmonic oscillators. Here's a displacement of the nth harmonic oscillator, weighted with some coefficient A. And this S lives in the system Hilbert space. So within the full Hilbert space, the system plus bath Hilbert space, we know how to write down the equation of motion of the density matrix. Well, that's just given by our von Neumann equation we wrote down a second ago. But I can write it down in a leading way, in a way that we'll make use of, namely separating out some reference evolution from that due to the coupling. So the reference piece is 1 over h bar, evolution due to the system plus bath, without the coupling. Sorry, that should be a B. And this perturbation that acts because the system and bath are weakly coupled. Again, we're going to imagine that V is small. So that the system and bath are weakly coupled. If they're strongly coupled, we probably have no right to imagine that we can monitor the system independent of the bath. But if the coupling is weak, maybe we can deduce the influence of the bath on those well-defined degrees of freedom of the system. All right, so we will imagine that this coupling is weak, such that to a good approximation, the evolution is determined just by the evolution of this reference operator. So to do that, it behooves us to introduce a representation which encodes the evolution of the density operator under the action of that reference propagator. And so that is to move into what is known as the interaction picture. That is to define operators like the density matrix through a similarity transformation. So I take my original density matrix and I dress it with propagation, with propagators that know about the time evolution under some h naught, where h naught is the part of the Hamiltonian that doesn't know about the coupling. In this case, the system plus the bath. Now I need to do this for all of my operators. So in addition to the density matrix, I can define a coupling operator in the so-called interaction picture. in the same way. I'll denote everywhere that I'm using this interaction picture with a subscript capital I. This is essentially a gauge, a means of watching the phase evolution of the density matrix with reference to the phase that it would evolve with under just H naught. Now, if you plug these operators in to our von Neumann equation, what you will find is that the evolution of the interaction picture density matrix is given by just that additional evolution due to the coupling between the system and the bath, namely just from the interaction picture system bath coupling operator acting on the interaction picture density matrix. So you all should show that. It's reasonably straightforward. You can do it either by plugging in what we've just defined as the interaction picture density matrix and interaction picture coupling, and showing that that is consistent with the original von Neumann equation. Okay, so this equation now has isolated those terms due to the perturbation. So let's integrate it. So now the density matrix at some time t. So this is a first order homogeneous equation. It's solved by an integrating factor, like we've seen before. But things are a little bit more subtle because these v's are now explicit functions of time. The integrating factor has a integral over time. Acting on the interaction picture has explicit time dependence also. And now the fact that vi at t does not necessarily commute with vi at a different t means that there is some time ordering operator that when I expand that exponential takes care of the fact that the v's don't commute with each other. What that means in practice is that if we were to Taylor expand this, again, we're imagining that v is small, so the argument of that exponential is small. If we were to expand it to second order, so the zeroth order is just rho at 0. The first order is a single time integral from 0 to t over some dummy index t prime. The action of this propagator on rho. And to second order, I now have two nested time integrals. The outer one from 0 to t and the inner one from 0 to t prime. And two factors one at t prime and one at t double prime of that interaction between the system and the bath. So this is an expansion in that coupling to second order. So it's an approximate evolution equation for the integrated evolution of rho I, but it's going to be valid if V is small enough that we can truncate that expansion at that order. Okay, so now we're in a position to ask about the explicit evolution of just the subset of degrees of freedom we care about. So we have already introduced this in pictures. Let's define our reduced density matrix, that which spans only the Hilbert space of the system. In the interaction picture, let's define that reduced density matrix as sigma. Principle has a time dependence as an explicit trace over the full density matrix over those bath degrees of freedom. This is our integration over the bath degrees of freedom. To get the time dependence as defined through this tracing over the bath, we can trace this integrated equation over the bath on the left and the right sides. That will give us an initial condition, less I times an integral, the trace over the bath of what I get when I act the perturbing part of the evolution onto the full density matrix. So now not only is the density matrix under the trace operation, but it's the action of L on that LV on that density matrix. So I don't know what that is naively. And analogously, the 2-time integral piece, I can write it down through this trace operation. But I have to work to evaluate it. Indeed, this tells us that generally the evolution of the reduced degree of freedom, the reduced density matrix, depends on the full density matrix, because that is what's evolving in time on the right-hand side of that equation. So to go forward, we need to make an additional approximation. So to separate the dependence of sigma, the reduced density matrix, on the full density matrix, let's assume that the full density matrix can be written as that reduced density matrix tensor producted to an equilibrium bath density matrix. This approximation is known as the Born approximation. It is essentially a statement that there are no correlations, that there is no entanglement between the system and bath, that their density matrices are separable. It's also an assumption that the bath begins in equilibrium. This is consistent with our linear response approximation to the extent that the system and bath interact weakly. I never move the bath far from its equilibrium position. So within this factorization, now we can evaluate those terms living under the integral. So for example, if I took this first term, trace over the bath, a single action of our LV on rho. Well, what I mean by that is a trace over a commutator 1 by h of V in the interaction representation with rho. That's a trace over the bath 1 by h Vi, plugging in the Born approximation. That is sigma I rho B less sigma I rho B Vi. Vi is a, so some more space. Vi, remember, was a linear product of a system operator S and a bath operator X. So S, as well as sigma, do not live in the bath Hilbert space. So they can be both taken out. They can be both taken out of that trace operation. Those are all in the interaction picture. I'll have the first term that looks like that, and a second term that is the exact same, given the cyclic invariance of the trace operation. So that trace over the sum AN XN is just an equilibrium bath average. So that whole thing is just the thermal expectation of that sum. let's define that as some lambda. It's just some number. It's no longer an operator. It tells us about the weighted displacement in equilibrium of those oscillators. That's a number that I could very easily set to 0 if I set the centers of my oscillators to 0. But let's write it down for completeness in case we were to want, for some reason, that those equilibrium positions not be 0. So that whole term then is just a dressing of the original system operator S by this factor lambda. This should remind you a bit of the renormalized force we got in the generalized Langevin equation. This is a static contribution. It's time independent, as it's just a thermal average. So it is only going to change, if finite, the relative eigenvalues of the system Hilbert space. Okay. The second term can analogously be evaluated. So if we look at our second term here, it's got two actions of that. So let's actually denote this first. Okay. Now working with this term. So that is a trace over the bath. From the first LV, I get a commutator of VI at T prime. From the second LV, I get a commutator of VI at T double prime. From the Born approximation, this is sigma I, T double prime, and rho B. So if I unravel that, again, noting that V is this combination of S's and weighted sums over X's. So that's the first term in the inner commutator. And there we are. Again, S lives only in the system Hilbert space. So it and rho B commute. Sigma and the X's commute. So I'm left with Si T double prime sigma I. Separable from weighted sum over the displacements times rho B. The second commutator makes this a little bit more complicated. Note that under that trace operation, I have quantities that depend on 2 times. So looking at just say the first term, I will have a trace over the bath, SI interaction T double prime, SI interaction T prime. Sorry, one of those should be double prime, one of these should be prime. Sigma I. That's all of the system pieces, and separated from it is a sum over n, an squared, xn operator interaction picture T prime, xn interaction T double prime times rho b. I can neglect, so in principle there should be a squared sum, so I should have sums over n and m. We will assume that the operators are independent, such that any average over unlike positions is just going to average to 0, or just average to their uncorrelated value. So that's the first term. I'll get a second term which looks similar. Trace over B. Now in the other ordering, so now I have this now times, so that was, these were all at T double prime. I'll get a squared, and now an xn interaction T prime, which commutes with S interaction at T prime. Again, S and sigma all live in the system Hilbert space, so they can be taken out of the trace in the bath. So I'm left with SI interaction T prime SI interaction T double prime sigma I T double prime, and a trace over the bath rho B, a sum an squared xi in xi T prime T double prime. That's first term. The second term, sigma I T double prime SI T double prime SI T prime. And now trace over the bath, rho B an squared, and a different time ordering of the x's. So this object here is a thermal average I know that because it's a trace over all the bath degrees of freedom weighted by their equilibrium weights. And it's a function of 2 times. So that's a time correlation function. It's a time correlation function of a sum of all the bath time correlation functions, each weighted by that coupling A. And so we can define this as some bath correlation function here of t double prime less t. You know, these are operators, so this is distinct from CB at t prime less t double prime. But those two are related through a complex conjugation, as we've discussed in our other discussions of quantum time correlation functions. Okay, so putting this all together, that whole term can be compactly rewritten now as a bath correlation function and a single commutator Si prime with Si double prime sigma I double prime minus the complex conjugate of that bath correlation function and a single commutator Si t prime, now sigma I t double prime Si double prime. These are, of course, only some of the terms in this nested commutator. But this is in all of them. Okay, so we can put all this back together. We get that the time derivative of sigma of I, the reduced density matrix in the interaction picture, is equal to a static term that tells me how, on average, the system is affected by the coupling to the bath, and a time-dependent term that has information about the dynamics of the bath and thus how it influences the system. Oof. All right. So we have a static contribution from the bath to the system dynamics and a time-dependent contribution that is determined explicitly by just a bath correlation function, what we've denoted CB here. This is all still in the interaction representation. if we were to take it back out of the interaction representation, it's reasonably straightforward to show that the time dependence of the reduced density matrix, now in the Schrodinger representation, has a coherent part of its evolution due to its system Hilbert space, its system Hamiltonian, dressed by lambda some shift of its eigenvalues through the action of its static average, to the static average of the bath action on the system. And in addition, this complicated time non-local piece, which encodes the actual dynamics of the bath through its bath correlation function. Invoking the time translational invariance of the bath correlation functions, I can write this at 1 time t prime, putting in all of the associated complex phases for going back into the Schrodinger representation. Many of them will cancel, but some will not. Those two will. All right, there's one term, and then I have minus CB complex conjugate in the different ordering. Okay. Whew, that looks pretty nasty for 2 reasons. So first, we do have a completely determined equation. So sigma on the left depends only on sigma on the right. Those are the only dynamical variables. It is parameterized by the original system Hamiltonian, this operator S that tells us how the system talks to the bath, and a function CB, which is the total bath correlation function, but it's non-Markovian. In much the same way that our generalized Langevin equation was. Sigma of t depends on sigma of t in the past, as it is convolved with those functions under that integral. So an additional approximation we could make is to assume that the bath relaxes very quickly, in some sense, such that we can get rid of this non-Markovian structure to the equation. This is a little more subtle in the quantum case, because of these things that live right here. Those complex phases that dress the system operators. Even if the bath is slow, there's no guarantee that they're slow relative to those fast phases in the system. Indeed, if the energies are separated far apart for any reasonable system, there will be large energy gaps in addition to small energy gaps. Those large energy gaps can't possibly be important to the dynamics. The excitation into those energies is very unlikely, but nevertheless, it spoils applying a kind of naive Markovian approximation. It wouldn't be justified to just pull out the whole sigma of t from that integral. So to do this, it's a little simpler to work. So right now we have an equation of motion for this whole density matrix. It's a little more easy to understand the Markovian approximation if we look at the equation of motion for the individual elements in sigma. So let sigma AB be the A-bth element of the density matrix. Taking the bra and Ketz and sandwiching the whole right-hand side is a little bit cumbersome algebraically, but one can do it. And one gets minus I omega b as the frequency beating just from the system, the original system eigenstates. So again, if this is a population, a diagonal element of the density matrix, there's no frequency. There's a term from the static coupling to the bath. And now all of those terms under the time integral things get a little complicated because of the number of resolutions of the identity you have to introduce. So now I am a 2-index quantity on the left will depend on products of 2 index quantities with sums over 2 additional indices, introduced C and D. Working these all out. Products of those linear coupling operators, sigma, in a complex phase owing to that dressing that we just highlighted there. I have a minus another set of bath operators from that commutator. All right, those are the first terms due to the bath in the forward time. The complex conjugate of the bath waits a second set of terms. Whew. All right, that's quite an equation. Look at all those indices. All right, but those are what they are. So we have combinations of two matrix elements multiplying different components of the density matrix underneath those time integrals multiplied by Bath correlation functions. So those products, the Bath correlation function, those two system operators, define a 4-index quantity let's call it RAC. It's so tempting to do DC. ACCD, a tensor, 4-index tensor, as 1 over h bar squared from the factor out in front, that Bath correlation function at time t prime, and those products of system operators, SAC, SCD. That'll simplify our notation a little bit. Take this whole monster and introduce those there. All right, so everywhere these things show up, I can put that R factor. All right, this one will be at RACDB. Here I have an RACDB complex conjugated to the complex conjugation of that Bath correlation function. And from this one, an RCDB, also complex conjugated. All right. Now that looks a little simpler. So in order to make this Markovian approximation, we need to figure out how to deal with, oh, no h bar outside anymore. Need to figure out how to deal with these sorts of terms. Let's see if I can grab that. Okay, so that sigma dB is going to have some fast oscillation just due to the fact that there are these frequencies from those off-diagonal elements. So let's reintroduce the interaction picture. That would say that sigma dB t minus t prime in the interaction picture is sigma I t minus t prime with a phase let's do that just at one time so I can fit it all on this line. there's a phase there that is minus I omega dB. So if I do that, I get a minus I omega dBt. That's a function of t, not t prime, so it comes out of the integral. I have my 4-index tensor quantity, gross. I have this interaction picture representation of I, C, B, t prime, and now plus I omega dB at t prime. So now I've factored out that rapidly moving phase. So within the interaction picture, the additional contribution from the dynamics of sigma due to the coupling, that is something that in the gauge in which I'm moving with potentially a fast phase is something that presumably moves slowly. So the Markovian approximation now can be done faithfully. So now approximately, I can assume that sigma I changes slowly. So I can pull it out of the integral relative to the decay of those Bath correlation functions dressed with those potentially high frequency oscillations. Now note that those frequencies are just differences of energies. So that whole quantity can be rewritten as e to the I omega dc at t prime. This was, I didn't put the, I dropped the dB, dB, dB. This is now back into the Schrodinger representation. And so this whole term is that element of the density matrix. And now, if I assume that those decay quickly, I can take the upper integral to infinity. And what I've got now is an integral from 0 to infinity, this tensor quantity, which is a function of time, reflecting the Bath correlation function, multiplied by a complex phase. Well, that's a single-sided Fourier transform, the so-called Fourier Laplace transform. So what that gives me now is this 4-index quantity evaluated at that frequency, omega d c. So now this is just a number. It's a fairly complicated number. I have to compute a Bath correlation function. I have to integrate it in time, and then I evaluate it at that specific frequency. So if we now go through this and do that same set of steps for each element, or for each one of these terms, this one and this one, that one and that one, I will get an equation of motion for the a-bth element of the density matrix, which is now pretty compactly represented and Markovian. It's still kind of complicated, has these additional sums. Whew. All right, there we have it. So the equation of motion for the reduced density matrix has a piece which is a static coupling that just renormalizes the frequencies of the system, the original system. And in addition, there are now transitions that the bath mediates within the system. These R's are kinetic quantities. They have in general real and imaginary parts. The real parts are those that transfer populations between different states. The imaginary parts are contain additional phase information. This equation is known as the Redfield equation. Originally derived by Redfield in the context of NMR, thinking about the dephasing of spins in solutions. It resulted from a handful of approximations. First, a so-called weak coupling approximation. We worked within our linear response, assuming that the bath responded linearly. We made a so-called Born approximation that not only does it respond linear, but it stays in equilibrium, and there is no initial entanglement between the system and the bath. The density matrices were separable. And finally, a Markovian approximation to make this equation time local. So there's some additional discussion in the notes, but to see that relaxation, consider that these tensor elements, which are known as the Redfield tensor, can be decomposed into real and imaginary parts. And if I was to write the equation of motion, say for just the diagonal element AA, and only include those terms due to the coupling between the diagonal elements, what I would find is that I can write this evolution equation in terms of just the real parts of that tensor. Clean that up just a little bit. So the population in A, the diagonal element sigma AA, changes in principle with some additional non-diagonal terms, but the diagonal terms are real numbers multiplying other populations in C, or losses due to real rates of transitions out of A. So indeed, essentially, we've just done a whole bunch of work to find that we've computed the rate along the diagonal of the density matrix to go from site A to site C, which is just given by a matrix element squared, factors of h bar, and an integral over the Bath correlation function, Fourier transformed and evaluated at the energy gap between those two states. This is exactly what you would have expected from something like Fermi's golden rule. It says that the Fermi's golden rule rate, the time-dependent perturbation theory result, to go between A and B, or A and C in this case, is the coupling element squared, and then a resonance condition that says that the energy that the bath takes in to mediate that transition has to be there in the bath. So if I looked at the frequencies within the bath as encoded by the Fourier transform of the Bath correlation function, that if I look for the frequency that is resonant with the AC transition, that as long as that's there, and as long as there's density at that frequency, the bath can mediate that transition. So Redfield theory, it said, includes all first order processes, first order bath mediated processes, reflecting the linear response approximations we've made to get at this equation. Those connoisseurs of quantum dynamics will note that Redfield theory also describes not only rates of transfer between populations, but the dephasing of coherences. That's described in the notes, but since we're over time, I won't go any further there. You can read about it there in the notes, and I'll go ahead and leave you here for the day. But what we've done, what should not be lost, is that we've derived the quantum analog of our Focker-Plunk equation, the equation of motion for the probability of observing a system in a specific state. Now, a state quantum mechanically includes both on-diagonal elements of some density matrix as well as off-diagonal elements, which have no classical analog. We did that first in a closed system, finding the von Neumann equation, and then opening the system up to allow for the exchange of energy with a bath. We've derived the so-called Redfield equation. All right, so I'll leave you there. I look forward to seeing you all in the small group discussions.